Refraction and refractive index. Note the pencil on the screen. This indicates places where you may want to take notes, highlighting key areas. Key areas. Absolute refractive index of a material is the ratio of the sine of an angle of incidence in a vacuum or air to the sine of the angle of refraction in the material. This follows on from work that we did within National 5. The refractive index of air is treated as the same as that of a vacuum and is equal to 1. Situations where light travels from a more dense to a less dense substance. Refractive index can be found from the ratio of speed of light in a vacuum or air to the speed of the material and the ratio of the wavelengths. Variation of the refractive index with frequency. What we will do today is investigate the ratio of angles of incidence and angles of refraction for light passing from one medium to another. This is the experiment that you would carry out in order to determine the refractive index of a perspex box. You must be able to quote this experiment and describe how it is used. First of all, a perspex box is placed on a white piece of paper and an outline traced around it. Then a normal is drawn in at midpoint B, remembering that a normal is drawn at 90 degrees to a surface. The incident angle theta A is equal to 10 degrees. We measure the angle theta P, which is the refractive angle in the perspex. Then we repeat for other values of incident angle. This information is then recorded in a table. Once we've calculated the sine of the angles, the angle of incidence, theta 1, and the angle of refraction, theta 2, we work out the ratio of sine theta 1, the angle in air, to sine theta 2, the angle in the perspex. The ratio of sine theta 1 to sine theta 2 is a constant when light passes obliquely from medium 1 to medium 2. That is, when the light passes through completely. The absolute refractive index, n, of a medium is the ratio of sine theta 1 to sine theta 2, where theta 1 is the angle of incidence in a vacuum, or air as an approximation, and theta 2 is in the medium, i.e. n is equal to sine theta 1 over sine theta 2, and this relationship is on your relationship sheets. Note that the refractive index of air is 1. And therefore we can write the relationship of the ratio of the sines of the angles of incidence, the sine of the angle of refraction, as a ratio of the refractive indices. That is, n2 over n1 is equal to sine theta 1 over sine theta 2. The refractive index measures the effect the medium has on light. The greater the refractive index, the greater the change in speed. Remember from National 5, refraction is the change in speed of light when moving from one medium to another. So if we have light moving from air or a vacuum into a more dense medium, the refractive index will be larger and the speed of light within the material will be smaller. The absolute refractive index is always a value greater than or equal to 1. When calculating the refractive index, we use a graph showing the relationship between sine theta 1 and sine theta 2. The refractive index is equal to the gradient of this graph. You've used this technique before, for example, when you were working out resistance using a graph of voltage against current. Note that the different colors are refracted through different angles, and that's due to their different frequency. The refractive index of light within a material depends on the frequency or color of the incident light. For example, the refractive index of the medium for blue light is greater than that for red light, and that's because blue light has a higher frequency or a shorter wavelength. This is why when white light passes through a triangular prism, it's broken up into the colors of the rainbow. Each of the different colors of light refracts by a slightly different amount, and therefore the signs and their angles of refraction are slightly different. Note, wavelength and velocity change during refraction, but frequency does not change. That is, the color remains constant. The frequency of a wave is unaltered by a change in medium. So when light passes from medium 1 to medium 2, we can use the following relationship, which is noted on the relationship sheet. Sine theta 1 over sine theta 2 is equal to lambda 1 over lambda 2 is equal to V1 over V2. And all of these are equal to the refractive index n. Example 1. In this diagram, we see light incident onto a plastic block and it is refracted. This is a common diagram seen within the higher, particularly in the multiple choice questions, and we need to use the information in the diagram to find the refractive index. First thing we need to determine is the angle of incidence and the angle of refraction. Please note that the angle of incidence is measured between the normal and the incident ray. The angle of refraction is measured between the normal and the refracted ray. So although you may have these quoted angles within your question, you have to know how to calculate the angles of incidence and the angles of refraction. This is a common problem-solving question and would be A-type. So we need to find theta 1, the angle in air, and theta 2, the angle in the material. Theta 1 is equal to 90 degrees take away 30, which is 60 degrees. Theta 2 is 90 degrees take away 54, which is 36 degrees. And with these, we can work out the ratio of the sines of the angles. N is equal to sine theta 1 over sine theta 2, which is equal to sine 60 over sine 36, which is 1.47. As we expect, the value of the refractive index is greater than or equal to 1 and has no unit. It's simply a ratio. In example 2, we need to calculate the speed of light in glass of a refractive index of 1.50. We should already have in our heads here that because we're going into a more dense medium, which we can tell because the refractive index is 1.5 and greater than 1, which is a refractive index in air, we expect that the speed is going to decrease. This is a very common question, and here the examiner assumes that you know the speed of light in air is 3 times 10 to the 8 meters per second. If you couldn't quite remember that, that information is also on the datasheet on the front of your paper. In example 2, instead of using the ratio of the sines of the angles as we did in example 1, we're using the ratios of velocities. V1 over V2 is equal to the refractive index n, which is equal to 1.50. V1 is the speed in air, so we substitute that in, and then rearrange to find V2, which we find to be 2 times 10 to the 8 meters per second. A similar example could be done with wavelength. What you're expected to be able to do is to be able to determine the angles of incidence and the angles of refraction, and use these to calculate the refractive index. Know that the refractive index is equal to the ratio of the wavelengths in and out of the material and the speed of light in and out of the material. You should also be able to describe the experiment used to determine the refractive index of material, and know that the gradient of the graph of sine theta 1 over sine theta 2 is equal to the refractive index.